Hello guys, welcome once more to another video in our YouTube channel. This video I'm going to be recording while writing. Alright, so if it does not appear very clear, make sure you increase your YouTube resolution to maybe 480 or 720 so that you see it clearly. I don't really know the orientation of my camera, so maybe it might not be vertical, it might be horizontal in a reverse direction, but just pardon me for that. All right, so we are going to be looking at functions. I'm going to summarize functions in this video. This is mathematics. Anything you have to know about functions, I will put it in this video. So under functions, I'll give you a brief summary. First of all, we are going to look at domain of definition of a function. Then after domain, we are going to look at domain alongside with codomain. Okay. Now after this, we are going to look at let's say injectivity. Yes, injectivity of a function. After injectivity, we look at surjectivity of a function. Then this will turn up to bijectivity of the function. Now, after this, before looking at subjectivity though, we are going to look at the inverse of a function, okay? Because for you to check the subjectivity, you must get the inverse of the function. Then from here, we are going to look at composition, and then we look at sketching a function. So these are the things you are going to be looking at. All right. Okay. I think this video will not really be the best in terms of quality, because I believe if you're a follower of this channel, if you're a subscriber of this channel, then you realize that I've never most at times, in fact 99.9% of the times, I do my videos digitalized. So I use my computer to do the videos. But to summarize all of these things in a computer is so much work. So that's why I decided to just do a brief summary. I think what is more important is the explanations and what you are going to gain after watching the video. So make sure you stay till the end. Now, let's talk about the domain of definition of a function and the codomain. So I'm not going to to complicate things, because this is pure mathematics. This is not further maths. All right. So a function is basically, we can say it is a mapping from one set to another. All right. So these two sets, maybe domain and codomain, are linked by the function f. Now this function is taking elements from the domain and associating them with elements of the codomain. Now the elements of the domain, we call those elements the inputs, while the elements of the codomain, we call those elements the images. Now B is the image of A, which means that if the function is eating A, it's going to produce B. Alright, it's like maybe when you eat arrow, or I don't know, your best meal, you're going to defecate. So you are the function eating arrow. Arrow is like the input, alright, and then now physics is the defecation. And you cannot eat what is not in your system. You are not going to defecate anything. For example, what you are eating must be in the domain of definition of, for example, we can say, if you eat something you don't like, you realize that though you are going to defecate, but just think about eating something that you don't like, or maybe eating poison, you are going to die, right? So because poison, your system does not recognize poison as something that is supposed to be in its domain. So that's basically what a function is doing. All right, it's taking elements from a set called a domain to another set called a codomain. Now, a function is a one-to-one mapping, or a many-to-one mapping. So this element this element E can also have the image as B, as well as the element A can also have the image as B. Alright, but the element A cannot have two different images. Okay, that is now just basically a mapping. Alright, so a function is peculiarly a one-to-one relation or a many-to-one relation. Those are just the basics. Alright, now let's dive into how do I find the domain of definition of a function. Basically, I'm just going to list some functions and show you how to get their domains of definition. So if you have a rational function, alright, you have a rational function maybe I give you f of x equal to 1 divided by x plus 2. Now this function is defined whenever the denominator is not equal to 0, so x should not be equal to negative 2, because we cannot divide by 0 in mathematics. Alright, so that's it for rational functions. Like I said, I'm more concerned with math guys, because in further maths they'll still give you this type of function, and the domain will not be x given from negative 2, because they'll try to include some other functions involved. Now, so whenever you see a rational function in math, the domain is x not equal to negative 2. A rational function when the numerator is also a polynomial. Let me be specific. Okay. Now, what about square root functions? The square root of maybe x plus 1. Now, this function is defined when x plus 1 is greater or equal to 0, which means that x is greater or equal to negative 1. Okay, so that's the domain of definition of this function. Okay, why? Because the square root is defined when the interior is always positive. Okay, now I think I'm going to end there. When we talk about maybe the ln function, for it to be defined, the x here must be positive and also different from 0, and so on and so forth. Okay, we concentrate less on domains because domain will not really carry much marks. So let's go to injectivity. How do I show that a function is injective? So a function is injective if f of a, okay, is equal to f of b. It means that a is equal to b. So if you want to show that a function is injective, you just have to show that f of a equal to f of b implies a equal to b, where a and b, so a and b are all in the domain of definition of the function. Let's take an example and try to show that a function is injective. Okay, let us say I define you a function f. Alright, now I write arrow minus 1, 2, arrow minus 2. I say x is associated with x plus 1 divided by x plus 2. Then I ask you, show that this function is injective. Now, first of all, let us identify the key properties of this function. Arrow minus 1 is called the domain of definition. Arrow minus 2 is called the codomain. Alright. Now, this arrow minus 1 means that this function is defined for all. No. Let's put arrow minus 2 here and arrow minus 3 here. Because the domain of this function is that x plus 2 is not supposed to be 0, so x is not equal to negative 2. Now, this function, his or her domain, if we call the function a person, is arrow minus 2, which means that the function is defined for all. Is negative 2, sorry. The function is defined for all real numbers excluding negative 2. Okay, because when the denominator is 0 when x is negative 2. Now the codomain could be anything. Alright, so it all depends on if the function is surjective or also have a well-defined codomain. Okay, so how do I show that this function is injective? So I just need to show that f of a equal to f of b implies a is equal to b, where a and b are in the domain of the function. Then I've shown that the function is injective. Now this is what I have to show. So this is like p implies q, alright, which is read as if p then q. So we actually know that p is true. Then we are going to use now to show that q is also true. So I begin. F of a is equal to f of b. What does this mean? I come and replace x with a. A plus 1 on a plus 2 is equal to b plus 1 on b plus 2. Now we cross multiply. We have a plus 1 times b plus 2 equal to a plus 2 times b plus 1. Now expand together. We have ab plus 2a plus b plus 2 equal to ab plus a plus 2b plus 2. ab cancels ab, 2 cancels 2. Now we have to subtract a on both sides and b on both sides. 2a minus a is a, alright, and then 2b minus b is b. So you see, we have proven that f of a equal to f of b implies that a is equal to b. So the function is injective. So f is injective. Now injective also means that it is 1-to-1. Okay. So in the GC, however it asks to show that it is 1-to-1, it means you're showing that it is injective. Now let us see how we can find the inverse of the function. So How do I find the inverse of this function? I'll start by letting y to be equal to f of x. Okay, now this means that y will be equal to x plus 1 on x plus 2. Then I'm going to make x the subject of the formula. So I'll multiply y times x is yx, y times 2 is 2y equal to x plus 1. Then I bring the x together, then I subtract 2y on both sides, then I factorize x, I have y minus 1 equal to 1 minus 2y. Then I make x a subject, so you have 1 minus 2y divided by y minus 1. That is it. Now, since we let y to be f of x and we are supposing that the inverse exists, it means that f inverse of y is actually equal to x. Now, f inverse of y is x and x is 1 minus 2y on y minus 1. So there is no doubt that f inverse of y will be equal to the 1 minus 2y on y minus 1, because that f inverse of y is equal to x. So since x and y are variables, we can now automatically deduce that f inverse of x is equal to 1 minus 2x divided by x minus 1. That is the inverse. Now, what is the range of this function? The range is the domain of definition of the inverse. Now, what is our inverse function? Our function is defined, our inverse function is 1 minus 2x divided by x minus 1, I suppose. Yes, 1 minus 2x divided by x minus 1. So for this inverse to be defined, what should happen? X minus 1 should not be equal to 0, because that's a denominator, which means that x should not be equal to 1. So the domain of the inverse is the set of real numbers excluding 1. Alright, now the function itself was defined like this: arrow minus negative 2 to arrow minus 3. So let us talk about surjectivity. So a function is surjective if the range is equal to the codomain. Now, what is a range? The range is a domain of the inverse and it is a set of real numbers minus 1. What is a codomain? Set of real numbers minus 3. Since set of real numbers minus 1 is not equal to set of real numbers minus 3, then f is not surjective. Alright, if I defined the function and the codomain was real numbers minus 1, then it is going to be surjective. Okay, now another name of surjectivity is the function is onto. So injectivity 1 to 1, surjectivity onto. Okay, so according to our program, we have done injectivity, surjectivity. If you are injective and surjective, you are bijective. We have seen the inverse. Now let us see let us first of all sketch before going to the composition. Okay, so let's analyze, or in fact let's just use this little space here to do composition of the function. Or maybe let me just give an exercise and then you answer in the comment section. So let's say we have a function f. The function f is from arrow this right up till arrow 2. Now x is associated with, let us say we have x plus 2 on x minus 1. Now first maybe verify injectivity, verify surjectivity, and then verify bijectivity. Voila, so that's it. Okay, so let's now go to sketching of a function. So for me to sketch the function in question is x. Let's go back to x plus 1 on x plus 2. So x plus 1 on x plus 2. First of all, I start by finding the domain of definition. Alright, now we said that the domain here is x not equal to negative 2, but it's better to write this domain as an interval. So if I go to the number line, alright, and I pin negative 2, if you're not equal to negative 2, then you are greater than negative 2 as well as you are less than negative 2. So this is x less than negative 2 union x greater than negative 2. If you want to write it as an interval, you are going to say x is in the interval. You begin from minus infinity, you arrive minus 2, then you continue from minus 2 and you arrive positive infinity. If you have a problem with this notation, how to write it, comment in the comment section. So I'm going to do another video, maybe 2 or 3 minutes, just drilling on how to write the interval notation. Now, after writing this interval notation, we need to get what we call the limits at the bounds of the domain. Now, these are the bounds: minus infinity, minus 2 from below, means you're approaching minus 2 from the left, minus 2 from above, you're approaching it from the right, and positive infinity. So let's go. The limit as x goes to minus infinity of f of x is equal to the limit as x goes to minus infinity of x plus 1 on x plus 2. Now, this is just going to give us 1. Why is it 1? Because the numerator is a polynomial and the denominator is a polynomial. So the degree of the ratio of two polynomials is just the degree of the ratio of the coefficients of the highest power of x with that highest power of x. So here, the coefficient of the highest power of x here is just x, is x raised to the power 1, right? So I just carry the x. Okay, so this x term is controlling the whole numerator. This x term is controlling the whole denominator. So the limit of everything here is a limit of x over x, and x over x is 1, so the limit is 1. Now let me take kind of, maybe let me try to drill you. Let me give a how can I put it? Let me take something else and see if you can get the limit. The limit as x goes to plus or minus infinity of maybe x squared plus 1 on 2x squared plus 2. Now, this numerator is controlled by x squared. So I'm just going to have the limit as x goes to plus or minus infinity of x squared divided by, this denominator is controlled by 2x squared. 2x squared. 2x squared, x squared cancels and we get half. Okay, now this numerator is controlled by x squared at plus or minus infinity, alright? So that's why I'm just replacing the numerator with x squared, because as x is going to plus or minus infinity, this one is negligible, so we just concentrate with this guy. Now, if you have the limit as x is going to plus or minus infinity of 2x plus 1 on x on 3 minus 1. Now, this will just be equal to the limit as x goes to plus or minus infinity. The numerator is controlled by 2x and the denominator is controlled by x on 3. The 3 will go up and meet the 2 to give us 6. So we have 6x on x, the x cancels and we get 6 as the answer. So that was just a demonstration. Okay, so let's get back to our limit. So the limit at minus infinity or even plus infinity is the same, it's equal to 1. Alright. Now, we have two limits left. The limit as x is going to negative 2 from below of f of x, okay, is equal to the limit as x is going to negative 2 from below of x plus 1 on x plus 2. Now, let me also write the limit as x is going to negative 2 from above of f of x, which is equal to the limit as x is going to negative 2 from above of x plus 1 on x plus 2. Now, what are these limits? Okay, so these limits, negative 2 from below, okay, it means that you're approaching negative 2 from the left. It is a number that is less than negative 2, but very close to negative 2. Alright, so we can take, when you are here, for example, you are maybe negative 2.00001. Now, you have to use your calculator. Replace it and punch. Maybe take negative 2.00001 plus 2. You are going to have something like negative 0.0001. Now the numerator, you also take the negative 2 point that and you add to 1, you're going to have a negative number. The two negative signs will cancel and you realize that the denominator will be going to 0 and the numerator will be going to a certain number, so everything will be going to plus infinity. Alright, now this guy here, you also replace, this man will automatically be going to minus infinity. Okay, after replacing, so take your calculator and replace x with negative 2.000000001 and you punch. You realize that when you punch in the first case, the result will be giving you a very big number, and when you punch in the second case, negative 2 from above is a number bigger than negative 2 and very close to negative 2. Maybe we can call it negative 1.999999. You replace and punch, you realize that you'll be going to a very big number, but in a negative sense. Okay, so a very, very small number. Okay, now after getting the limit, now we need to look at the asymptotes. Now in mathematics, we just have two types of asymptotes, the vertical. And to get the vertical, we can either check from the domain, we just solve the denominator equal to 0 and we get the vertical, or we check the limit. The vertical asymptote says that if the limit as x is tending to a of f of x is equal to plus or minus infinity, then x equal to a is a vertical asymptote. Alright, so in this case, the limit at minus 2 from below and from above is plus or minus infinity. So x equal to minus 2, so x equal to minus 2 is a vertical asymptote in this case. Okay, now what about horizontal? If the limit as x is going to plus or minus infinity of the function is equal to a real number, then this real number is a horizontal asymptote. In this case, the limit at plus or minus infinity is 1. So it means that y equal to 1 is a horizontal asymptote. Now, after looking at the asymptotes, we have to go on to the monotony of the function. So monotony, look at the monotony. Now looking at the monotony, we have to differentiate first of all. So f of x is equal to, we have x plus 1 on x plus 2. It means that f prime of x will be equal to, now we keep the denominator, first of all square the denominator, right? We are using the quotient rule. Now we need to keep the denominator and differentiate the numerator. When we keep x plus 2 with differentiate x plus 1, we just get 1, so we are going to have x plus 2 minus. Now we have to keep the numerator x plus 1 and differentiate the denominator. We are just going to have the x plus 1. Now it therefore means that f prime of x is equal to x minus x is 0, 2 minus 1 is 1, so we have 1 divided by x plus 2 all squared. Now if f prime of x is greater than 0, then f is strictly increasing. If f prime of x is less than 0, then f is strictly decreasing. Alright, now if f prime of x is equal to 0, then f is constant. Okay, so in this case, and when you're constant, we now find the turning point. So let's now check the sign of f. F of f prime of x, sorry. Our f prime of x is 1 divided by x plus 2 all squared. Okay, now is it positive or is it negative? That's the question we have to be asking ourselves. Now this is a ratio of two functions. Okay, the denominator is already positive because it is squaring. No matter what is inside here, once we square, it is positive. Okay, now so the sign of everything here will depend on the sign of the numerator because we already know the sign of the denominator. Now the numerator is positive because it is 1. Positive over positive is positive, so everything here is positive. It cannot be equal to 0 because for a ratio to be equal to 0, the numerator has to be 0. But in this case, the numerator is 1. So first of all, we are going to say that f prime cannot be 0. Alright, because 1 is not equal to 0. Okay, now we clearly see that f prime is always greater than 0. And since it is always greater than 0, then the function is always strictly increasing. Now, so they are not turning points clear because the numerator cannot be 0 and the function is always increasing. Alright, now the next thing we do is the intercepts. Let's get the intercepts. Now, when x is equal to 0, what is y? Y is equal to half. Now, when y is equal to 0, what is x? If I equate this man to 0, okay, what do I have? If I equate this man to 0, I cross multiply 0, I have x plus 1 equal to 0, so x is equal to negative 1. So the first intercept, when x is 0, y is half, and the next intercept, when x is negative 1, y is 0. Those are the intercepts. Now the next thing to do is the variation table. Variation table. Now this table is very nice and very a little bit complicated to draw, but follow me. Now the variation table, we are imputing all the informations we have had previously. Okay, so we have x, we begin with x. Okay, then we write the x is basically all the values that concerns x. So we begin with the domain minus infinity minus infinity, then We have minus infinity. We have minus 2. Okay, we have minus 2. Then we have positive infinity. Now I'm going to tell you why I kept a bigger space here. I kept a bigger space here because there is 0 and there is also negative 1. All these values concern x. If there was a turning point, you also need to put those values here. So we put there is minus 1 first, then there is 0. Alright. Now we draw vertical lines passing through all. Now we go to minus 2. Since it's a vertical asymptote, we try to cancel it. Let me try to draw it here. So we have x, okay,